the first thing that we want to establish here is what a covalent bond actually is. Okay, and there are two types of covalent bonds. There is a sigma bond, okay, which is a direct end-to-end overlap of orbitals. Okay, concentrated between the two nuclei. So this is the most direct way a bond can occur, the shortest distance between the two nuclei, right in between them. Okay. So that's sigma bond. So every first bond, essentially, every first bond between two atoms is a sigma bond. So you can assume that every bond, no matter what type of bond, single, double, triple, the first bond between two atoms is always a sigma bond. That's default. Never a doubt. But to have additional bonds, you have to take advantage of your p orbitals. And so that involves what's called a pi bond. Okay. And that is what's called a sideways overlap of orbitals with a density above and below the plane of nuclei. I don't think you're really going to have to get in that detailed about the definitions here, but I'm kind of presenting those so you can kind of see what we're talking about. But so pi bonds are sideways overlap or parallel. So they're not in between the nuclei. They're kind of equidistant from both nuclei. And so that's why the pi bond is weaker. So it is weaker than a sigma bond. That's why a double bond isn't double the strength of a single bond, because a pi bond is already inherently weaker. Okay. A double bond will consist of one sigma bond and one pi bond. A triple bond will consist of one sigma bond and two pi bonds. So every time you have a multiple bond between two atoms, it's an additional pi bond that's present. You never have more than one sigma bond between two atoms. Okay. So understanding that brings up an issue with the way bonding works. Okay, because we've established that it's an overlap between orbitals. Well, then how do you explain something like CH4? Okay, because experimentally you get information about CH4 that doesn't match up with the way atomic orbitals work. Okay, because when you think about atomic orbitals, okay, when you think of something like CH4, carbon has 1s2, 2s2, 2p2. So it's this, and this. And in the s and the p, you have one s orbital and a 2py orbital, a 2px orbital, and a 2pz orbital that are 90 degrees from each other, just like x, y, and z are in a mathematical graph. And these are the atomic orbitals that have electrons in them. Okay. Now, the issue is this. Okay. Experimentally, we notice that when we measure things, we have 4 equal bond lengths and 4 equal bond angles. So our experiment says that we have 4 equal bond lengths and 4 equal angles. Can you derive that from these 4 orbitals? Can you derive 4 equivalent bond lengths from these 4 orbitals? The answer is no. Okay, so scientists had to come up with an explanation for what happens when these orbitals start bonding with other structures. What, Mohammed? Okay, so because these are all 90 degrees and this is its own sphere. So what had to happen is that all 4 of these orbitals had to turn into 4 hybrid orbitals that were equivalent. So that's what scientists suggested or proposed based on their experimental data. And a hybrid orbital is essentially the mixing of atomic orbitals in an atom. Okay. And so what scientists realize is when carbon bonds to hydrogen, there's no such thing as an s orbital. There's no such thing as a p orbital. They're all mixtures of part s and part p into hybrids, all equivalent shapes. So I'm not going to make you draw this, but I'll put this diagram in here. And so this is what scientists deduced that these orbitals look like. Okay. Oh, sorry. So what they said was no longer do you have an s orbital and 3p orbitals. You have these 4 identical hybrid orbitals that are a mixture of s and a mixture of p orbitals. And this works out, bless you, for 2 reasons. 1, they're all identical now, so they're the same bond length. And 2, there's another issue with the way the electrons in carbon are organized. Okay? Are the valence electrons in carbon originally organized in a way that you could bond 4 times? Like, are the valence electrons bonded so you can bond 4 times with these? They are not. Because the s and the p orbitals have different energies. So what this also does is it takes the 2s and 2p and makes them all equivalent. And these are known as sp3 orbitals because they are a hybrid of 1s and 3p orbitals. So sp3. That's what the notation means. It's taken 3p orbitals and 1s and made them all equivalent. So that way you can put 1 electron in each and then they can bond. Yes, Mofe? Yes, it's okay. Yes, sure. Yes. Yes. So because these shapes, the way they are right now, cannot form this. Because you got different shapes, different lengths, and everything like that. So because this was what they measured, they realized these aren't the way things bonded. So what had to happen is those shapes had to transform and change to allow things to bond equally. So what they did was they took those shapes that I drew here and realized the orbitals that bonded were different shape than they are normally. And that's this shape right here. Yes, I would say. And like, but it is a pretty concrete theory, yes. Tyler.
What causes this to occur, though? Why don't we just always say there's no point having sp orbitals, we just always hybridize?
Because hybridization only benefits an atom when it's sharing electrons with another atom. When it is by itself, it's better to have separate atomic states where you can have 2 electrons in the s and 6 electrons in the p, as opposed to having 4 all at a higher energy state than these 2 down here. So this only benefits when you're trying to bond and share electrons with other atoms. That's why. Um, I mean, there is some inherent energy that change when a bond is formed. So yes, I guess you could argue that. Okay. And so when you bond, you form hybrid orbitals. Now, that's not exactly the whole kind of story here, because what happens here is the H bonds here, the H bonds here, and the H bonds here, and the H bonds here. Okay. What you need to know is that only sigma bonds and lone pairs hybridize, because pi bonding actually happens in a different way. Okay, only sigma bonds and lone pairs hybridize. So if you add up how many sigma bonds and how many lone pairs you have on an atom, you can figure out its hybridization. Okay. So let's say you had 3 sigma bonds and 1 lone pair. That means you would need 4 hybrid orbitals, which means you would need to take 4 orbitals and hybridize them. So you'd take 1 s and 3 p's. So the hybridization of that would be sp3. Let's say I had 2 sigma bonds and 1 lone pair. That would mean I need 3 hybrid orbitals. So what orbitals would I use then? S and how many p's? 2. So guess what? It's sp2. Do y'all see what I'm doing to get the hybridization notation here? All I'm doing is figure out how many hybrid orbitals I need, and I take that number of atomic orbitals for my hybridization. So if I need 4, I take my S and my 3 p's. So it's sp3 hybridization. If I need 3, I take my S and 2 p's. Yes, Marcus? Yes. Oh, sorry. Not exactly. Okay. Because for expanded octets, you obviously have to have more orbitals to hybridize, which then we'll talk about in a second. Okay. Mohammed, question? Of this, no, around 1 atom. Yeah. So hybridization is specifically for an individual atom in the structure. When we say the hybridization of a molecule, we usually mean the central atom. I think, yeah. You answered your own question. So, okay, questions about this. So, what I want you to do from this is just say, okay, if I want to know my hybridization for an atom, I just look at how many sigma bonds and how many lone pairs I have, and that's my hybridization. That's what I want you to connect together. Now, the idea is, for example, CO2. We talked about CO2 earlier. It looks like this. Okay. So this carbon, how many sigma bonds does it have? 2. Because each carbon oxygen has 1 sigma bond. And how many pi bonds do you have? 2. Okay. So how many lone pairs does it have? None. Oh, just on the carbon. We're talking about just carbon. Sorry. That carbon has 0 lone pairs. So therefore, it needs how many hybrid orbitals? Just number first, Mofe. How many hybrid orbitals do we need? Quantity. 2 plus 0? 2. You're just adding numbers together. Okay, because these are the things that participate in hybridization. Remember we were talking about earlier that only sigma bonds and lone pairs hybridize. So when we look at this carbon here, it has 0 lone pairs and 2 sigma bonds. So therefore that carbon needs 2 hybrid orbitals. So the hybridization around that carbon will be what? sp1. That's it. Okay. I would, just to be careful. Yes, Mohammed. It's really the pairs of electrons that are involved in those types of, yes. But, so the question is, well, what are these pi bonds? Okay, those pi bonds come from unhybridized p orbitals. So the way you generate pi bonding is you leave p orbitals alone, because What's great about those p orbitals? Well, they're already parallel to each other, so they can share electrons across that plane already. So when you have a pi bond, you don't need to hybridize them, you leave them alone. And I'm going to show you what that visually means in a second. I'll show you what CO2 looks like. Because I have a good diagram of CO2 here, so you can kind of understand what's happening here. Okay. This is what CO2 looks like, orbital-wise. Okay, let me show you what we've been talking about so far. Okay. This area here, this green and yellow, represents the hybridized orbital that's sharing electrons, the sigma bond. That's the overlap between the two nuclei. So one sigma bond here and one sigma bond here. Okay, but that carbon needs to have two pi bonds, one with each oxygen. So what does it do? It has one p orbital, that's the Y one, that parallels with this oxygen's p orbital to form the double bond. And then there's another one that's sideways here that lines up with this oxygen to form the double bond here. So that's the pi bond, that's the sigma bond. That's the pi bond, that's the sigma bond. That's what's actually happening with these orbitals. And that's why it's a linear shape. No, it does, because these yellow ones are the hybrid orbitals. So they're in that linear plane. So what you need to remember is this: sigma and lone pairs form hybrid orbitals so that they are prepared to bond. But pi bonding happens with unhybridized p orbitals, so they don't count toward your hybridization. So carbon in the CO2 is an sp1 because it has two hybrid orbitals and no lone pair. No, two sigma bonds and no lone pairs. Okay. Okay. Let's say we had something like ozone. And we were just talking about this oxygen in the middle here. Okay, the one in the center. Okay. How many sigma bonds does it have? Two sigma bonds. How many pi bonds? One. How many lone pairs? One. So thank you, good job. Three hybrid orbitals. Okay. So what is the notation for hybridization when you have three hybrid orbitals? sp2. That's it. Wasn't sure if he was getting up to celebrate or like I was like, okay, Mofa, you just added. Okay, that's not like okay. All right. So that's how you figure out hybridization. Ginevra. No. They would just generally ask you what the hybridization is. Okay. And you just write sp2. That'd be a 1 mark question. Identify the hybridization on this molecule. Or what they'll do in multiple choice is they'll label like 3 different molecules and then ask you the hybridization around each atom. I'm sorry, 3 different atoms in the same molecule, and they'll say what's the hybridization around this one, and this one. Yes, Mohammed. Yeah, so in resonance, for example, in ozone, that double bond goes back and forth. So each oxygen has to have a p orbital that's unhybridized. And so they all happen to be the same axes. So then they overlap like that. Yes. So what happens with ozone here is that each oxygen, sorry, I don't know how to draw this best. So because each of them have to be available to double bond, the electrons go between this unhybridized p orbital, and they're all the same directions. They all line up. That's why the system of drawing the dotted lines represents that, but I don't like drawing that for your Lewis dot structures. It's just not accurate. So all of them have the same p orbital that's unhybridized, so they all line up. That's why the double bond can resonate. Benzene's the same way. Remember we drew that in organic? We showed all the p orbitals were all lined up, and so that's why it circles around in that ring for that. So that's that concept there. Okay. Now, what Marcus said earlier was something that's very important, and that is expanded octet. Okay. An expanded octet has two requirements, generally speaking. One, has to have 5 or more valence electrons. To do it without a dative bond, you have to have an expanded octet. And two, it has to have an empty d sublevel, which means it has to be in period 3 or greater. Because the d sublevel exists in the energy level 3 and higher. Or greater, I should say. Yes, Sophia. Oh, so I thought I saw a hand. So, things like phosphorus, sulfur, chlorine, arsenic, selenium, bromide, all of those moving down that group can have an expanded octet because it has an empty d sublevel. Now, some of the d sublevels are filled, but the outermost one's empty because we don't fill that one in the order in which row it's on. Remember, we fill the d that's one less than the row it's on. So, like, if you look at something like, let me just pull up here our table. If you look here, phosphorus has an empty d sublevel because it's on the third energy level and there's no electrons in its 3D. Because you don't fill 3D until after 4s. So bromine has electrons in its 3D, but doesn't have electrons in its 4D because 4D doesn't fill till much later. So all these atoms actually have an empty d sublevel, even though there are some electrons in the d. So why does that expanded octet matter? Why does that d sublevel matter? Because those are the orbitals that hybridize to allow more than 4 bonds on center. So if you have 6 hybrid orbitals, what do you think your hybridization would be then? If you have 6 hybrid orbitals, what would it be? No, there's not 5 though, Noah. How many p's are there? How many? Yes, sp3d2. Because you can only have a maximum of 3p, that's why expanded octet has to have a d sublevel. Sometimes they'll write it as d2 sp3. It doesn't matter. There's not a difference between writing it that way. Huh? Technically, there are theoretically structures that have 7 hybrid orbitals, but for our purposes now, stability-wise, 6 is the maximum. So if you have 5 hybrid orbitals, it would be sp3d1. You don't have to write that 1 there, but I write it anyways just to make sure. And so when I do hybridization, I just write out my orbitals, sp, p, and then dd. And then I just, whatever number of hybrid orbitals I need, I count from left to right. So if I need 4 hybrid orbitals, then that's sp3. If I need 5 hybrid orbitals, it's sp3d1. If I need 6, then it's sp3d2, and that's the maximum that it can go. So you just count from left to right until you get all the ones you need. And hybrid orbitals are also equivalent to our charge centers. So back to geometry, whatever number of charge centers you have is your hybridization. So even if you have 3 bonds and 1 lone pair, or 2 bonds and 2 lone pairs, or 4 bonds and 0 lone pairs, you all have a charge center of 4. Because 2 plus 2, 3 plus 1, or 4 plus 0 is 4. So all of them have the same hybridization. So if you look here, because all these have the same charge center number, they're all sp3. And all the ones that add up to 3 are sp2. All the ones that add up to 5 are sp3d1. So the number of charge centers is the same as sigma bonds plus lone pairs. So you can relate those both to each other. So things that are tetrahedral, trigonal pyramidal, and bent with 104, they're all sp3 because they have 4 charge centers. It doesn't matter if it's a lone pair or a bond. Here. So let's talk about those shapes because we haven't done the expanded octet shapes yet, and that's the kind of main thing here. Okay, we'll try to get through this quickly here. But if you have 5 sigma bonds and 0 lone pairs, then you have 5 charge centers, which means a hybridization of sp3d1. And that shape, I'm going to draw it this way, even though it's kind of hard to see on the side because all the other shapes make more sense that way. This is trigonal bipyramidal. Okay? Because this Y makes a triangle, and then each triangle goes to this point and goes to this point. So it's trigonal bipyramidal. It looks like this with your fingers. So this is your Y. The fingers touching are your Y, and then my palms are the other 2 atoms. So you see how it forms like 2 pyramids here? Do y'all see that here? 2 pyramids. Yes or no? Okay. I'm just doing it sideways because it helps with all the other shapes. If you have 4 sigma bonds and 1 lone pair, you still have 5 and sp3d1. But what I do is then I take off the top line. So what I have left is this, which is, guess what? Seesaw. Oh, bond angles, you only need to know for your electronic geometry. So this one is 90 and 120. You don't need to know the seesaw bond angles. They're a little bit less, but that's okay. Three and 2. Now, I've taken away this top line. This is where I need to get you to understand this. I've taken away the top line, okay? The next lone pair has to be as far away from the other lone pair as possible. So, which of these is the farthest away from this line here? Which of the remaining lines is the farthest one away from here? The ones on the bottom, okay? Because they're 120 degrees away from each other. So, I'm going to take away one of those ones on the bottom. Okay, what shape is that? T shape. Looks like a T.
It's not a straight T.
It actually is. It's just, it's in the z-axis, so you're kind of looking at an angle here. If you want, you can cover these 2 instead, and it's very obvious that it's a T shape. But I kind of start from the top and work down. And guess what? If you have 2, well, which line is the furthest from these 2 lines that we've taken away? The other bottom line, because they're all 120 degrees from each other. So then what you're left with is this, which is linear. Okay, well, because you look scared. Okay, so that's linear, and that's 180 degrees. It's because the lone pairs are equidistant and equal angles from each other. So for linear, what you have to imagine is that one lone pair is up here, and then one lone pair is here, and one lone pair is here, and they all cancel each other out because they're 120 degrees from each other. So the x and the y coordinates all cancel each other out. That's why it flattens. It's vectors, right? Yes, Pancho. I think it's just given. I never had to do that, so maybe they do it now, but in some conceptual chemistry class. But no, you don't really need to prove that. Okay. Sorry, we're kind of going through this quickly, but I still want to talk about formal charge. Okay. Huh? There's not a 1 or 4. That's just linear. It would just be 2 atoms. No, no one's going to ask you that shape. Okay. 6 and 0. The way I draw it is this. Line, X, through that. Okay? Because it's like a mathematical grid, X, Y, and Z axes. So this is called octahedral. Okay. Why is it called octahedral? Because even though it's only 3 lines, because there are 8 faces. Because if you imagine this, there's a face that forms with these 3 lines, a face that forms with these 3 lines, a face that forms with these 3 lines, and a face that forms with the front 3 lines. That's 4 faces on the top, and there's 4 faces on the bottom the same way. So it's called octahedral, which is all 90 degrees. 5, 1. Okay. Doesn't matter which one you take away when it's 1, but I just start on the top. So if I take away the top one, what's the shape that's left? Pyramid, what base? Square pyramidal. That's why I draw it like this. So this is square pyramidal. Yes, because we're talking about molecular geometries here, Pancho. Yes. Because all of these here have the same electronic geometry of octahedral. Because they're all 6 charge centers. But molecular geometry is what I'm talking about here. Now, from this structure, remember the lone pair is on top. Where's the furthest lone pair from the top one? The bottom. So guess what's left? Square, planar. Exactly. Hence why I draw it this way. Because the lone pairs are on top and bottom, they repel each other equally, so it flattens back out. What about 3 and 3? Okay. Does it matter which one I take away from 3 and 3? Not really. So I'm just going to take away that top one. T-shaped. And now, I took away this top one. Which one am I going to take away next? The bottom one. So guess what's left? Linear. So the 4 lone pairs actually cancel each other out because all the vectors cancel out and you're left with linear, which is 180 degrees if you really want to get down to it. What, Maha? What? Shut up. We're not doing 1 and 5. Okay. Technically, like, if you want to be honest about it, you can't really have a 1 and 5 because there's no point in having an expanded octet if you only bonded to 1 atom. So that's really the truth behind it. Still, that's an expanded octet. That'd be 10 electrons around the atom. Okay, so what have you added to your shapes here to memorize? Okay, so if you draw these 5 shapes, you'll be able to figure out all the rest of your molecular geometries. So SL, you incorporate linear, this one, and now you incorporate this and this. 5 shapes help you remember. Wait. What? 15 shapes. 14 shapes. No, 15 shapes. Because we've done 9 here, and then we had 6 from SL. So if you know these 5 shapes, you can figure out all 15 molecular geometries you need. Yeah. Minimize what you have to memorize. Okay. And remember what I do is I always block out the top one, and then I keep blocking away from the top one. So here, I block top, then I block this, and then I block this. Yeah, essentially. So this, you block top, furthest, 3, 4, linear. Yeah. Well, and tetrahedral. So the only time, this is what I was talking about polarity before. Remember how I said in SL that if you have a lone pair, it's always polar? In expanded octet, there are times when you have a lone pair and they cancel each other out. Like these linears here. So that's where it's tricky. Like, so these linears are actually nonpolar because the lone pairs cancel each other out. And like in square planar, they cancel each other out as well. So this is where with HL, you can't just say if you have a lone pair, it's automatically polar. Because if the lone pairs cancel each other out, then it's not polar anymore. That's what you have to be careful about. So again, let me say that one more time. So in SL, if you have a lone pair on your molecule, it's automatically polar. In HL, there's some expanded octets where the lone pairs cancel each other out, and it's not polar anymore. So like, for example, here, this linear one, all 4 electron pairs cancel out. That's why it's linear. So it's not polar anymore. I guess the rule of thumb, I don't even know what I'm trying to say that. I guess if you want a rule, you would say any molecule that has a lone pair that's not linear or planar is polar. I guess if you want to make a rule up, you would say any molecule with a lone pair that's not linear or planar is polar. That's a safe rule if you want to make a generalization. So any molecule that has a lone pair or lone pairs that's not linear or planar is polar. What, Mohammed? Correct. Hence why I worded it that way. Okay, one more thing and then we'll be done. Okay. Formal charge. Okay. Now, remember how I showed you how to do Lewis structures with the math number and the test number before? It was easy the way I did it because the atoms were all the same on the outside, so you could tell when there's resonance and not. But here's an issue. Let's say we have something like SCN minus 1. Okay, we can still do the math number and test number, but we'll run into an issue and you'll see what I mean. Okay, S is 6, C is 4, N is 5, and the negative 1 is 1 more. So that is 16, which means 8 pairs. So when you draw the test structure out, you draw it like this. So there are 10 pairs here. So that means you need to transfer and change 2 bonds. The problem is this. Those 2 atoms are not identical. So there is a priority in which you add the double bonds. And you add the bonds to. And you have to figure out what that priority is. And that's what formal charge is. Because I could make it this. I could make it this. Or I could make it this. Those are my 3 options. And so the way I differentiate and find the best structure is I look at what's formal charge. And formal charge is essentially what is the charge of the atom relative to its standard state. Okay, so what is its charge relative to its standard state? So I'll define that here, kind of. So formal charge, and I'll kind of use the IB definition here. Okay, the charge an atom would have if all atoms had the same electronegativity. So assuming that all the atoms were sharing electrons equally, what would its charge be based on that? Now, you want 2 rules for this. First rule, you want everything closest to 0. That's your first rule. So if you're trying to select the best one, everything closest to 0. So the numbers like -1, 1, and 0 is better than -2, 0, and +2. So you want everything as close to 0 as possible. If there's still a tie, you want the negative charge on the atom with what kind of electronegativity? Where would you want the negative charge to be on? The highest electronegativity. So the negative charge on atom with the highest. Oops, what was that? Okay, with highest electronegativity. So that's your tiebreaker. So to do correct, yes, yes. If they tie on the first one, use tiebreaker. So how do you calculate formal charge? Now I'm going to give you an equation that's a little bit different than maybe what the book says. So choose one and go with it. I hate fractions and hate halves, and so this is what I do. I for formal charge, I do valence electrons, okay, minus bonds minus lone electrons. So a lone pair is 2 lone electrons, in case we're counting for this, okay? So a lone pair is 2 electrons. So valence electrons minus bonds minus lone electrons. Because remember, we're assuming everything has the same electronegativity, so if you have a bond, each atom gets ownership of 1 electron. Yes, Tyler?
So if you can just clarify, the bonds is like a double bond, you count that as 2.
Correct.
And then lone E is just not the pairs, right? Just the single.
Correct. So a lone pair would be 2 electrons. Okay, so correct, and that's what we're going to do now to show which one's the best structure, the most ideal structure. So in this scenario on the left, S here is 6 minus 3 minus 2. So that's 1 plus. C is 4 minus 0. So that's 0. N is 5 minus 1 minus 6. So that is 2 minus. Give you a second to write that down. Yeah. Yeah, because what you'll see is that, like in some books, they'll say valence electrons minus 1/2 the bonding electrons, because like a bond is 2 electrons. So they'll be like, oh, there's each bond is 2 electrons, so you multiply 1/2. Why? Just count the bonds, because each bond gives you 1 electron, right? So I rewrote it that way. They don't care as long as you get the right answer. It doesn't matter the way you calculate it. But just don't get confused if you see that in the book that says, oh, do valence minus 1/2 bonding electrons minus other electrons. Does everyone see how I calculated this here? And the overall formal charges should add up to the overall charge. And it is a -1 charge, so your formal charges are correct. Okay, the middle one. S is 6. Oh, sorry, I didn't draw all the lone pairs. So S is 6 minus 2 minus 4. So that's 2 minus. C is 4 minus 0, so that's 0. And then N is, wait, what? Oh, 0, I'm sorry. 6 minus 2 minus 4. Yeah, sorry. I was getting ahead of myself. So N is 5 minus 2 minus 4. So it's -1. Thank you, Mohammed. The last one is S is equal to 6 minus 1 minus 6, which is -1. Yeah. C is 4 minus 0, so that's 0. And N is 5 minus 3 minus 2, and that is also 0. Okay. Oh, I just forgot to circle. Like, yeah, sorry. Okay, that was not intentional. Okay, I don't know why I circled all of them to begin with. I just wanted to make it clear that that was the answer for each one. So like Amir said, there's a tiebreaker. The second and third one, and he's probably wondering how I heard him say that, but I hear everything. So the second and third one are the same in closest to 0. So you can rule this one out right away. But now the negative charge has to be on the more electronegative atom. And I'll double check, but I'm pretty sure that's nitrogen here. But if you don't know, go to your data packet and go to electronegativity right here. Wait, what'd you say? No, because that will always, if you're doing it right, they all should add up to the same number. Yeah, that's what I'm saying. But you cross it out because they weren't as close to zero as possible, Marcus. Yeah, you want everything as close to zero as possible. So here, N is 3.0, S is 2.6. So you will choose this as your optimal structure. Okay, because it follows these two characteristics, Tyler. One, oh sorry, everything is close to zero. So 0, 0, -1, and then the tiebreaker is if there's a negative charge. Yes, of the two. Yes, Ginevra. Yes, that is one way to do it. Correct. Yeah. So if you get like, I'm telling you this, if you get like a 5 or a 6 somewhere, you did something wrong for a formal charge because it should really be maybe maximum of 2. And like I've literally seen them have like a table that just says calculate the formal charge of each atom, fill in the blanks, and it's like a 4-mark question. So this is something that is an attention to detail that you need to know. Okay. Questions about this? Okay. So again, to wrap up, higher level, you have to know what hybridization is, how to figure out the hybridization of an atom, figuring out what a sigma bond is, what a pi bond is. They all relate to each other. Knowing your expanded octet requirements and your shapes of your expanded octet and their hybridizations, and then formal charge. Those are the things. Okay, that's it for today.